And okay, proteins. You've all heard of proteins, and um, these guys are a big deal in our body. We have millions of proteins in our body. You know, all the enzymes are all proteins. All the less than enzymes like insulin and stuff are polypeptides. Um, they're just all over the place. They really are. They're really, really important biochemical molecules. And what makes them unique are amino acids. And there are only 20 amino acids that are used to build those millions of proteins. Now, there are amino acids, and by a definition of amino acid means it's got an amino group plus a carboxylic acid group. However, in the proteins in our body, there's a unique part of each amino acid. And there's only one carbon in between the amino group and the carboxylic acid group. And because that is 1 over, they call that the alpha carbon. But there are also beta, gamma, etc., amino acids as well. The ones we're going to be focusing on for this unit are the alpha carbon amino acids. And that's the 20 amino acids that make up the 99.9% of the proteins. Okay, so we're looking at alpha carbon. Now the R can be goes from H. Let's see, goes from H all the way to very, very complex structures. Now, what I want to do is look at two amino acids as examples. Okay, cysteine, which is a really important one because of the thiol group. So we have the alpha carbon. Okay, and then here we look at glycine. I'm going to compare that to okay, so we have glycine, the simplest, and cysteine, which is one of the really important enzymes. And the reason is the this thiol group here can easily hook on to heavy metals. I'm going to talk about that later. And because of that, that's where mercury is bad for you. That's where lead is bad for you, is because it latches onto that cysteine amino acid and it latches on permanently. So if the cysteine amino acid happens to be part of an enzyme, well, then that enzyme stops working. And if that enzyme is an important enzyme, like cholinesterase, for example, that means your synapse chemistry across that membrane will stop working because the cysteine amino acid is latched onto that heavy metal. Okay, now what I'm going to talk about here is chiral carbons. Okay, so let's call this the alpha carbon. And this carbon here now has got 3 groups attached to it, so it can't be chiral. However, this guy has 4 groups attached to it. 1, 2, 3, 4, but they're not 4 unique. So this is not chiral. That means it's not D or L. Okay. All right, so let's look at cysteine now. Back, what I'm going to do is give myself some more room. Okay, so again, glycine is just glycine. It's neither D or L. However, if we look at cysteine, okay, so this carbon again can't be chiral because it only has 3 unique groups. And this is not missing an H, by the way. This is O minus. This is H plus. I'm going to talk about why this is the way it is in a minute here. However, this carbon is chiral, okay, meaning it has 4 unique groups attached to it. Okay, there's an H, NH3, CO, blah, 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 and then we have this guy down here. So all enzymes, all amino acids except glycine are chiral, which means they are D or L. Okay. Now, all natural amino acids are L. And remember, in carbs, the monosaccharides were either D or L. Most of them were D. Amino acids, they're L. Okay? Except for glycine, which doesn't have a chiral carbon in it, so it can't be D or L. Okay. And again, this particular amino acid, cysteine, is susceptible to permanent bonding with heavy metals. Now, we're talking about 20 amino acids, and they're in 4 groups. Okay. The first group I want to talk about are neutral, non-charged, and non-polar. Here's our good old glycine, and all these others are L amino acids, and they all have a chiral carbon in them. And the R group, these are the R groups now. Okay, the R groups are nonpolar. Okay, and then we can also have neutral, non-charged, polar side chains. And the reason why they're polar is because of the oxygen. And because sulfur is underneath oxygen on the periodic table, it's also very polar. Okay. Glutamine is another interesting amino acid that's related to glutamic acid, which is where we get MSG. Okay, so that's the second basic group. Now you need to know these four groups. And you need to be able to identify, if I gave you an amino acid, you need to be able to say, oh, this is a basic one and polar. And what I circle are the groups that make these particular amino acids polar and basic. Well, the fact that they're basic means they're automatically polar, but anyway, they go together. And then likewise, we have the acidic ones. And of course, this is glutamic acid. This is where we get monosodium glutamate from, MSG. And the problem with MSG is when you buy MSG, and I cook with MSG because I'm not affected by it. When you buy it, you get the D and the L forms. And as I mentioned before, the L forms are the natural ones. And this is why some people are susceptible to that one, the D form. So if you're susceptible to that in terms of allergic reactions or whatever, when you buy MSG, you're getting both of them, unless you spend a lot of money and get the L form. Okay. And this was the chiral nature I talked about a few minutes ago. Achiral means not chiral. Okay. Now, at physiological pH, our natural pH, except for our stomach and some other places, but in general, our pH is almost neutral, but it borders on the alkaline side. Because of that, all amino acids, the H goes over there. So we have something called a Zwitter ion. Zwitter means both charges. Okay. So the net charge is 0, but both a positive and negative charge exists on those amino acids, all 20 of them, no exceptions. Now, when you get an amino acid, let's take glycine, for example. And we put it in the stomach, pH 2. What happens is this is glycine. So this acid end of the amino acid protonates. In pH 704, so this is pH 704, this would be pH 2. So we need to be comfortable describing amino acids in different pHs. So this would be pH equals 704 or pH 9 or something like that, but right around neutrality, physiological pH. It's still alkaline, hence this is what it looks like. We get the Zwitter-ion form. Now, this is something very, very important, and you need to know this, okay? Something called an isoelectric point. Now, isoelectric means iso means the same. Electric means that there's no charge, no net charge. Okay, so what do we mean by that? Okay, here's two amino acids. This has got a +1 over here, -1 there, so the net charge on that is 0. +1, -1, 0 net charge. So when we adjust the pH, when we adjust the pH of amino acids, we are going to dial in a pH. Now, don't forget, there are 20 of these R groups. Some of them are acidic, some are basic, some are neutral. When we modify the pH of the environment that the amino acid is in, so that the net charge so in the net charge between balancing out the acidic R groups and the basic R groups are net charge is 0, then we've reached the isoelectric point. And we used to have, when I was teaching this class up in Washington, we had a lab where you determine the isoelectric point of an amino acid. And I'm trying to introduce that here, but because I'm adjunct and part-time, and they're not part-time people are not allowed to introduce new labs, although I've been doing that in our class, but it's been hard to get the isoelectric point lab in. Okay, so what's the big deal here? Okay, so if the isoelectric point of a amino acid or protein is not at the pH where charge is net 0, then the amino acid or protein is positive or negative. What that means is it's charged. If it's charged, then that means it's soluble in water. Okay? So we're going to adjust the pH on this amino acid or protein, because proteins are made up of amino acids. And when the net charge on that amino acid or protein is not 0, okay, when the charge is, and this somebody must be not net, not 0, then the amino acid or protein is positive or negative. That means it's charged or ionic. And that means it's soluble in water. Now, this is a big deal because this is how a lot of things, food-wise, and analytical techniques in biochemical labs is devised. Okay, for example, every isoelectric point, let me back up, every protein and amino acid has a unique isoelectric point. For example, casein is a protein in milk. Its isoelectric point is 4. That means when pH equals 4, net charge on the casein protein is 0 or not charged. So what happens at pH 4, because the charge is 0, it's not ionic. It precipitates out. Forms a solid. Now, for those of you who cook, who in here, how many, I don't know how many we have here, like 10 or 12. How many of you have made your own cottage cheese from scratch? Anyone? Okay, the way you make cottage cheese from scratch is to take your milk, so you take milk, add acid, pH goes down to 4. Now the casein is at its isoelectric point of 4, so what happens is you form curds. Curds are solid casein protein. And the liquid leftover is called whey. So to make cottage cheese from scratch, it's really easy. All you do is you take lemon juice or white vinegar, and you keep adding it. Usually you warm it to fairly warm, but not boiling or anything like that, just warm. And you keep adding this acid in, and all of a sudden the milk gets solid. You've got these solid pieces floating in the leftover water, which by the way is called whey. So what you end up with is curds and whey, and you filter out the curds and you have cottage cheese. That's how they make it. Now, interestingly enough, how do you make blue cheese, for example? Blue cheese is you let the milk sit out and let all the nice yeast floating around get into the milk. The yeast grow. What happens? They end up making these are lactobacillus. The bacteria make lactic acid. and they make more and more lactic acid till it approaches pH 4. And the curds form because it's now net zero charge. So this whole concept of isoelectric is very, very important. When the pH is above the isoelectric point, the protein or amino acid has a net negative value. When it's below the isoelectric point, the amino acid or protein ends up being positive value. Now this is the R groups. The R groups the R groups, depending on which combination of amino acids you have, depends on the combination of the R groups you have with the amino acid combinations will determine the isoelectric point. And one last thing I want to say about isoelectric points, which is as important as making cheese. If you have two proteins, I should say different proteins, they have different isoelectric points. So now we can manipulate which protein forms a solid and which one stays in solution by modifying the pH. By modifying the pH, one protein will come out of solution and the other will stay soluble. So it's a very, very, very common technique on purifying proteins is using the isoelectric points. Now, if the isoelectric points are the same, this does not work. Only if the isoelectric points are different. If they're the same, then you have to use some other techniques. There's a whole bunch of them. There's something called chromatography, and you can look at different ways that the protein interacts with different gels, and it just goes on and on and on. But this is the most basic and easiest to understand purifying technique of proteins, is looking at the isoelectric points of different proteins. Now, if we had like 5 proteins in there, all with different isoelectric points, we could just be modifying away on the pH, and we would get different ones would solidify out when their isoelectric point matches the pH of the solution. Very powerful technique. So this is why I starred this, is because it's so powerful of a technique. And hence test material. Okay. Okay, because they're ionic, big time soluble in water, ionic solids have high melting points, and they usually can precipitate out in solution. Okay. Okay, the only enzyme in mammals, there are other, not enzymes, amino acids, in other organisms, like yeast and crustaceans, etc. There are other amino acids, not the 20 that are typically in mammals. But cysteine is a frequent amino acid used in making up proteins on various organisms. If you oxidize thiols, you end up forming this here. So we go from cysteine to cysteine. Now, in your hair, some people have curly hair, some people have straight hair, and the degree at which your hair is curly depends upon cross lengths. We're going to get to cross lengths in a minute here. And this is one of the cross lengths that determine that. The cysteine cross lengths. They're very, very strong cross lengths because they're covalent. Hence, they're very strong. That's why you can wash your hair all you want and it's still curly. Wash your hair all you want and it's still straight because you have not broken the cross links of the cysteine amino acid unless you get a perm. Perms change all this, and that's why they are permanent. Okay, normally when this happens, notice the direction of the acid side. This, they usually show this in textbooks like this, but it's really like this on the right here, where the when the cysteines hook up, they're usually going opposite directions on the amino acid chain. Okay, so we've talked about amino acids. Now, when we have amino acids and amino acid together, we can form a amide linkage. And they call those peptide linkages. And that's how a protein or polypeptide is formed, by linking up amino acids via an amide linkage. A dipeptide has two amino acids with one amide bond, not two. So it's N minus one. 4 amino acids, that means there are 3 amide bonds. Now, in a test tube, if we were to put glycine amino acid along with alanine amino acid, we would end up with a 50% mixture of these two, because it's just by chance which ones hook up together. So statistically, the odds of glycine being on the left versus being on the right are 50-50. Enzymatically, that's totally untrue, because when we build proteins, we have very definite sequences in mind. You know, with all the RNA, the tRNA, the mRNA, all that stuff, determines the linkages. But in a test tube, there is no enzymatic activity to determine the order of the amino acid, only random chance. So we get 50-50, they're just two. So we've got starting with an amino acid is one amino acid. A peptide is a short length of amino acids. A polypeptide is less than 50, but greater than usually 4 or something like that. Let's say 4 to 50. And a protein is more than 50 amino acids. So just like with carbs, we have monosaccharides, disaccharides, oligosaccharides, and polysaccharides. With proteins, we have amino acids, peptides, polypeptides, and proteins. We have 4 levels of protein chains as well. Okay, so in biochemistry lingo, we have two ends of the polypeptide of protein. One end has got the amino function on it. The other end has got the acid end. So there's a N-terminal end and a C-terminal end. Notice whenever I've written amino acids today, I've always put the nitrogen on the left, the acid end on the right. That's just by convention. Okay, so because proteins and polypeptides can form zwitterions, and they form those on the N-terminal and the C-terminal ends. Um, like I was mentioning before with amino acids, if the net charge is 0, proteins clump together or form solids at the isoelectric point. And that's where net charge is 0. And as I was saying before, that's how cheese is made. Okay, there are two very, very, very generic protein shapes, fibrous and globular. Fibrous are long, string-like. You can think of examples would be like mussels, and they're very they're the most stable. And the least stable are the globular proteins. And this is where the enzymes come into play. So enzymes are globular proteins. They're very fragile. They're very sensitive to pH, the solvent they're in, and temperature. We have various levels of organization of proteins. We can have just a plain old protein, and all it's got is amino acid sequences or residues. Conjugated proteins have amino acid residues and something else. They call that prosthetic group. For example, hemoglobin, functioning around iron. Okay, so most of the time, proteins are hooked up with something else. It's pretty common. Okay, so now we're just looking at a pure protein with amino acid residues only, just a string of amino acids. Okay, we have 4 levels of we have primary, secondary, tertiary, and quaternary levels of organization of that long sequence of amino acids. Okay, the first level of structure is going to be just a long train-like sequence of amino acids. Now, the problem is that this is not stable once we get a long chain, though. That's one of the problems. So what happens to become more stable, the long chain goes into something called a secondary structure. Now what happens is we usually form a helix similar to a DNA helix for the same reason, and or a pleated sheet, which is kind of a combination. But the alpha helix looks just like DNA, and it has to do with the R groups, how the R groups interact. And depending on whether the R groups have hydrogen bonding going on, covalent bonding, dipole-dipole, these are all ways that the helix is formed. And this is what's going on. So once that the amino acid chain gets long enough, it starts becoming unstable. So what happens is we get these side chains that interact. And the interaction is using hydrogen bonding, covalent bonding, dipole-dipole. Those are the three ways that the side chains can interact to form the secondary helix structure. And again, think of everyone seeing DNA and RNA, depending on whether it's M or tRNA or whatever, but DNA is just a helix, and it forms a helix because of the side chain interactions of the base pairs. And we're going to talk about those in a little while, not in this unit, but in a little while. Okay, pleated sheets are horizontal sheets. And this is the way silk is kind of put together using pleated sheets. Now, in general, proteins are made up of a variety of organizational structures, secondarily, both the pleated sheet and the helix. And you have a combination of the two. Proteins tend to be very, very complex, very complex. And because of that, enzymes are complex as well. Now, these are the typical and there's actually one more here. There's, okay, so covalent, this is sulfur to sulfur, very strong, number one. Second is ionic. For example, if you had a negative acidic group and a positive nitrogen group, those are going to attract ionically, called a salt bridge, but it's also very strong. Hydrogen bonding, strongest IMF, and then there's another one, which would be a dipole to dipole, for example. And this would be 4, and this would be 5. Like 2 carbonyl groups, that would be dipole, dipole. So we've got covalence the strongest, LDF only would be the weakest. So you have 5 ways to do and these are all called crosslinks. And the crosslinks give a unique shape to the protein. Now, strong crosslinks are not affected by heat, solvent, temperature. Weak crosslinks are. So, for example, albumin, egg whites. What happens when there's heat? When you cook the egg, you're making a fried egg. The translucent albumin turns into an opaque white because the crosslinks were broken and reformed. Proteins, when they're in water, will form globules like fatty acids will form micelles. Similar interactions, the nonpolar hydrophobic side chains are in the middle. Are on the outside or the hydrophilic regions. So it looks just like a micelle with fats. Exactly the same concept. So we have primary, secondary, tertiary, and quaternary structures. Not all proteins have all of these. Some of them are only primary, some are primary and secondary, some are primary, secondary, tertiary, and some of them are primary, tertiary, quaternary. Just depends. Okay, so for example, hemoglobin. So we've got 2 and 2, so 4 chains. And then we've got some forces that keep the chains together. So it depends. And then you have typically with heme groups, you usually have an iron in the middle. Okay. So because we have an amide in a protein, they are susceptible to acidic and alkaline conditions, which will break them up into smaller peptides and eventually into amino acids. So if you're familiar with ceviche, this is what ceviche does. Okay, it takes a protein in a very acidic environment and it takes them apart. It denatures the protein. So if you have shrimp in your ceviche or fish, that fish becomes opaque, the shrimp becomes opaque, and it's like it's been cooked. Only it's not cooked via heat, though. It's cooked via protein denaturization. Protein digestion in your stomach with the enzyme protease hydrolyzes the protein. So in your stomach, pH of 2, proteases will take apart your proteins. So if you take an antacid, say you have heartburn, and you're just it's getting very uncomfortable, so you take an antacid and the heartburn goes away, that means you've neutralized some of that acid. After the antacid, the pH is no longer 2. The pH is 4, 5, or 6. However, a protease is designed to work with pH of 2. So your protein hydrolyzation process is affected in a negative way when you take an antacid. Okay, so denaturization means to change shape. From primary, secondary, tertiary, or quaternary. So it no longer is that original shape. Now, if this protein had biological activity, like an enzyme, it will no longer function in that activity. Okay, so what can denature proteins? Heat is a big deal. That's what cooking's all about. That's what cooking with microwave is, cooking with an ultraviolet light. All these put energy into the protein and it disrupts cross-links. That means they change shape on every one of these. We change the solvent. Now, if we're talking biochemically, the solvent's going to always be water, but if you're working in a non-mammalian or even non-organic environment, it's usually going to be water. But if we get out of that environment, we have other solvents, then the cross-links will be affected by the solvent. Strong acids or bases will hydrolyze the amide bonds. Soaps and detergents affects, again, the cross-links. These are all cross-link related. Heavy metals with the cysteine amino acid. These will all bind to cysteine. In which case, if these were involved in an enzyme, that enzyme would no longer function. We're not done already, are we? Okay, so that's proteins. Now we're going to be really taking proteins to much further steps as we progress through the days. Now we're not going to have, are there any questions, by the way, so far? You guys are always so quiet. Okay. Now we're not going to have a lecture because next week is going to be, the lectures are going to be on Monday is going to be a review on amines and amides. And then Wednesday there'll be no lecture. And Monday, Wednesday will be our tests next week. When we come back from Thanksgiving holiday, we're going to be getting into enzymes more specifically and how they work and how to name them, etc. So that's what we're looking at. And then from there, we're going to be looking at some metabolic processes, mostly metabolism of carbohydrates. And then we're going to wrap it up. So, okay. So are there any questions about anything? Okay, well, I guess I'll see the Wednesday folks in a little while. And Monday folks, have a very nice um, weekend, and I'll talk to you on Monday. Okay, so any other